Welcome to This Explainer. Today, we are uncovering the invisible, fundamental chemical forces that literally power absolutely everything around you. I mean, it's pretty mind-blowing when you realize that the exact same unseen forces driving massive industrial factories are churning away right this very second inside the microscopic cells of your own body. We're talking, of course, about redox reactions. To make sense of it all, we're going to break this down into 4 quick parts. 1. The world of redox. 2. The electron exchange. 3. The chemist's cheat code. And finally, 4 types of redox. Let's jump right in. Section 1. The world of redox. So, before we get bogged down in formulas and electrons, I want you to think about this. What unseen thread connects the battery currently keeping your phone alive, the rapid combustion happening inside a car engine, and the slow, inevitable rusting of a piece of scrap metal sitting in a junkyard? On the surface, they look like entirely unrelated things, right? What was genuinely fascinating is that all of these wildly different physical, biological, and environmental phenomena are driven by the exact same class of chemical transformation. Whether we're talking about the burning of domestic fuels, the electrochemical extraction of highly reactive metals, how wet and dry batteries operate, or even massive environmental challenges like the depletion of the ozone layer and the push for a liquid hydrogen economy, they all fall under this exact same umbrella. That brings us to Section 2, the electron exchange. You know, the way we understand this today isn't how chemists always saw it. Back in the day, they'd watch things rust or burn and figured, hey, this is literally just about adding oxygen to an element or maybe taking away hydrogen, which makes sense based on what they could see. But as the science evolved, there was this massive paradigm shift. Chemists realized oxygen wasn't always the main character. The true underlying mechanism is actually an invisible, simultaneous transfer of electrons. It's really all about who is losing electrons and who is gaining them. Today, we define these two halves of the exchange pretty simply. When an element or species gives up an electron, like, say, when solid sodium loses an electron to become a positively charged ion, we say it has been oxidized. Simply put, oxidation is the loss of electrons. But obviously, those lost electrons can't just float around in the void. They've got to go somewhere. So when a chemical species accepts that wandering electron, it undergoes what is known as reduction. Reduction is the gain of electrons. Now, let's talk about the roles these players take on. The specific substance that takes the electrons away, the one essentially forcing the other element to oxidize, is called the oxidizing agent. It's the acceptor. And here's the kicker. By taking those electrons, the oxidizing agent itself gets reduced. It feels a little counterintuitive at first, but it's absolutely crucial to understanding how this whole system works. On the flip side, we have the reducing agent. This is the generous species that donates its electrons, enabling the reduction of its partner. And by giving those electrons away, the reducing agent gets oxidized. They're basically two halves of a perfect whole. You literally cannot have one without the other. To actually visualize this invisible exchange, picture a classic chemistry lab setup. If you drop a strip of metallic zinc into a bright blue aqueous solution of copper nitrate, this amazing competitive electron transfer kicks off. Zinc acts as a highly active reducing agent, practically throwing its electrons at the copper ions in the liquid. Over an hour or so, the solution actually loses its blue color as the copper ions are reduced, turning into reddish, solid metallic copper that plates right onto the zinc strip. So zinc loses, copper gains. But with all these electrons constantly flying back and forth, especially in covalent compounds where they're just shifted rather than completely handed over, how on earth do chemists keep track of the chaos? Well, that takes us to Section 3, the chemist's cheat code. Chemists use something called oxidation numbers. You can think of this system like a really strict financial ledger. They apply absolute rigid rules to assign a numerical value to elements. For example, any free, uncombined element gets a 0. Fluorine is always a -1. Oxygen is almost always -2, and hydrogen is usually a +1. By assigning these values, we can easily track where our electron currency is being spent or gained across the reaction. And the real beauty of this bookkeeping system, it ties back to the periodic table so elegantly. It is so logical that an element's highest possible oxidation state aligns perfectly with its group number. It systematically scales from group 1, with a +1 state, all the way across to group 17, which can exhibit a massive +7 oxidation state. All right, moving on to Section 4, 4 types of redox. Now that we have the cheat code and can track the electrons, we can neatly categorize this vast, seemingly chaotic world of chemistry. Basically, every single redox reaction you will ever encounter, whether it's happening in a test tube or up in the atmosphere, falls into one of four structural blueprints: combination, decomposition, displacement, or disproportionation. Let's quickly walk through how they work. The first two are straightforward opposites. A combination reaction is exactly what it sounds like: elements joining together, like carbon combining with oxygen gas to form carbon dioxide during combustion. Decomposition is the exact reverse: compounds breaking back down into their elemental states, like liquid water splitting into hydrogen and oxygen gas. Quick caveat here, though: not all decomposition reactions are redox. The elements actually have to change their oxidation state for it to count. Next up is displacement. This is kind of like a competitive chemical dance. A highly reactive element cuts in and literally forces a less reactive element out of a compound, all based on a strict electrochemical hierarchy. This happens with metals, like our zinc and copper experiment from earlier, or even with nonmetals, like when highly reactive fluorine gas displaces oxygen from water. But the spotlight, in my opinion, really belongs to disproportionation. This is such a fascinating, almost paradoxical scenario. A single element in a reacting substance acts as both the donor and the acceptor at the exact same time. Take hydrogen peroxide, for example. The oxygen in the peroxide is in an intermediate -1 state. As it decomposes, some of that oxygen goes up to a 0 state in oxygen gas, while the rest goes down to a -2 state in water. It literally oxidizes and reduces itself simultaneously. How cool is that? To wrap this up, there's a single textbook quote that perfectly captures the universal law we've uncovered today: where there is oxidation, there is always reduction. Chemistry is essentially a study of redox systems. These two processes, oxidation and reduction, loss and gain, are inextricably linked in a flawless cosmic balancing act. You simply cannot have one without the other. I want to leave you with this provocative thought to explore on your own. If every single transformation of energy in the universe demands this exact, perfectly balanced exchange of electrons, what invisible electron trades are happening inside your own cells right now to keep you breathing, thinking, and living? Thanks for joining me on this explainer, and remember to keep questioning the invisible forces around you.